Welcome to Learning with Philemon. In this video, we will be looking at the three-dimensional geometry of molecules using VSEPR theory. In the covalent bonding video, we learned that nonmetal atoms bond with each other by sharing a pair or pairs of electrons. We saw how to draw dot and cross diagrams and basic Lewis structures. Methane, CH4, is shown here as an example. In this video, we will take it a step further, drawing the structures in such a way as to show the 3D geometry of the molecule and determine the bond angles. VSEPR stands for Valence Shell Electron Pair Repulsion Theory. This theory states that electron pairs around the central atom arrange themselves as far apart from each other as possible so as to minimize repulsion. For example, in gaseous beryllium fluoride, BeF2, beryllium is bonded to two fluorine atoms. The central atom in the molecule is beryllium. There are two electron pairs around the atom. Both pairs are part of a covalent bond, so they are called bonding pairs. These bonding pairs arrange themselves as far apart as possible because of the electrostatic repulsion of the electron pairs. Remember that like charges repel. The angle between the BeF bonds is 180 degrees. Note that the fluorine atoms have a complete octet, 8 valence electrons, after bonding with beryllium. Beryllium, on the other hand, only has 4 valence electrons now. Beryllium has an incomplete octet. Some elements can form stable compounds despite not having a complete octet. This will often be seen in elements such as beryllium, boron, and aluminium. Carbon dioxide, CO2, also has a linear geometry. Unlike beryllium fluoride, there are double bonds between carbon and oxygen, represented by the double line. When considering the geometry of a molecule, you must count the number of electron domains, areas where electrons are located around the central atom. Although there are 4 electrons here, they are in the same area, so the double bond counts as 1 electron domain. There are 2 electron domains around carbon, so the bonds arrange themselves at 180 degrees from each other. The next geometry we will discuss is trigonal planar. A typical example used is boron trifluoride, BF3. Boron has 3 valence electrons, which it uses to form single bonds with 3 fluorine atoms. Note that boron now has 6 valence electrons, and therefore is another example of an incomplete octet. Around the boron atom, there are 3 bonding pairs of electrons, and therefore 3 electron domains. If the bonding pairs arrange themselves as far apart as possible, the angle between the bonds is 120 degrees. The geometry is called trigonal planar because all the atoms lie in the same plane. This will become more clear at the end when I show the mole view simulation. In this next case, we have 3 electron domains, but one of the domains is a lone pair of electrons. In sulfur dioxide, SO2, sulfur forms double bonds with both oxygen atoms, using 4 of its 6 valence electrons. The remaining 2 valence electrons remain as a lone pair of electrons. Note that sulfur now has 10 valence electrons, which does not follow the octet rule. Elements above energy level 3 have d orbitals available to accommodate more than 8 valence electrons, which is called an expanded octet. It must also be noted that the structure of sulfur dioxide can be drawn using resonance structures. See the higher level videos for more on this. Around the sulfur atom, there are 3 electron domains, 2 bonding pairs, and 1 lone pair. The geometry is similar to the previously mentioned trigonal planar geometry. However, the lone pair of electrons has a higher electron density than a bonding pair. There is greater repulsion between the lone pair of electrons and the SO bond than between the 2 SO bonds. Therefore, the bonding pairs are pushed closer together than 120 degrees. The bond angle in sulfur dioxide is 119 degrees, but this may be different in other bent molecules. Now let's return to the example from the first slide. methane, CH4. At GCSE level, methane is represented with this diagram, where all the atoms are in the same plane, like in the trigonal planar arrangement. However, this is not the case. In methane, carbon uses its 4 valence electrons to bond with 4 hydrogen atoms. There are 4 bonding pairs around carbon, so 4 electron domains. For the bonding pairs to be as far apart as possible, they must have an angle of 109.5 degrees between them. In this diagram, the 2 hydrogens and the carbon are in the same plane. The other 2 hydrogens are not in the same plane, which gives the molecule a 3-dimensional shape. The bold bond indicates that the hydrogen is positioned in front of the slide, and the dashed bond indicates that the hydrogen is positioned behind the slide. This geometry is called tetrahedral. The next geometry is trigonal pyramidal. Let's use the example of ammonia, NH3. Nitrogen has 5 valence electrons and uses 3 of them to bond with 3 hydrogen atoms. The remaining 2 valence electrons remain as a lone pair of electrons. There are 3 bonding pairs and 1 lone pair, 4 electron domains around the central nitrogen atom. The geometry is similar to tetrahedral, which also has 4 electron domains, but the lone pair pushes the bonding pairs closer to each other. The bond angle is approximately 107 degrees instead of 109.5 degrees. The final geometry we will look at in this video is the bent or angular geometry. Let's use the example of water, H2O. Oxygen has 6 valence electrons and uses 2 of them to bond with 2 hydrogen atoms. The remaining 4 valence electrons remain as 2 lone pairs of electrons. There are 2 bonding pairs and 2 lone pairs, 4 electron domains around the central oxygen atom. The geometry is again similar to a tetrahedral, but now there are 2 lone pairs of electrons. Because lone pair repulsion is even greater than lone pair bonding pair repulsion due to the higher electron density of lone pairs of electrons, the bond angle is reduced even further to 104.5 degrees. These are all the geometries you need to learn for the standard level course. See the next video for more higher level content. A table I recommend all my students to use to memorize these structures is the following. Each row corresponds to a different number of electron domains, and each column corresponds to the number of lone pairs of electrons. Note that if a question asks for the electron domain geometry of a molecule, you can use the name in the first column. For example, all these structures in this row have a tetrahedral electron domain geometry. The molecular geometry is the specific geometry that considers the bonding and lone pairs of electrons. For molecular geometry, there is a distinction between tetrahedral, trigonal pyramidal, and bent. Note that the bond angle may vary depending on the source, so you will often just see less than 109 degrees instead of a specific value. Note also that there are 2 structures that are called bent or angular, one with 3 electron domains and one with 4 electron domains. A good way to visualize these geometries is to build molecular models, molymods. If you do not have access to a molymod kit, you can construct the molecules on the MolView website. See the link in the description. For example, you can construct a methane molecule and visualize it in 3 dimensions by pressing this button. Here it is clearer to see that 2 hydrogen atoms are in the same plane as carbon. 1 hydrogen is above this plane, facing us, and 1 hydrogen is below this plane, facing away from us. In conclusion, to determine the geometry of a molecule, you need to first consider the valence electrons of the central atom. Then you need to figure out how many bonding pairs and lone pairs there will be after bonding. This will help you determine both the electron domain and molecular geometry. Note that you will also need to consider the possibility of an incomplete or expanded octet. Finally, to determine the bond angle, you need to consider the repulsion caused between the lone pairs and bonding pairs around the central atom. From lowest to highest repulsion, we have bonding pair, lone pair, and lone pair repulsion. Thank you for listening. To consolidate your learning, I would suggest you attempt to draw different compounds or build them using MolyMods or the MolView website. Stay tuned for the next higher level video on more molecular geometries. If you haven't already, please subscribe for more content. Stay curious.